Okay, so good morning, everyone. Today we have the pleasure to have Dr. Yuanyuan Zhang from Fermilab, and she's going to talk about understanding cluster central galaxies with the past 8 million years and beyond. So thank you very much for accepting this invitation, and please, you can start.
Yeah, thanks for having me online. So I apologize in advance about my background noise because Fermilab is having some fire emergency right now. So, my ambience is not quite quiet right now. So I'm going to start with the introduction about the excellent opportunities offered by the backend survey on galaxy cluster science. After that, I will demonstrate this excellency with my own study about cluster central galaxies. Finally, I will also discuss the potential of high redshift cluster studies by DES, which I think is highly relevant to the topic of cluster central galaxies. So it is becoming a cliche now, but the fact worth it stressing again, that galaxy clusters are the largest gravitationally bound structures in the universe. So when we are given a large-scale structure distribution, galaxy clusters are relatively easy to be picked out. The background image here is the dark matter distribution from the Millennium simulation. When a yellow color in this figure means a higher dark matter density. So whenever we see a yellow blob connected to several filaments, we can be quite confident that we have found a galaxy cluster. So identifying galaxy clusters in observational data is not that straightforward, and some of my audiences here might know better about it. But basically, you still see clustering of matters at the spot of galaxy clusters. In optical data, you will see the clustering of galaxies. In X-ray data, you will see the hot gas emissions from galaxy clusters, which look like a big blob of emissions. So galaxy clusters are relatively easy to identify, and being the large, sorry?
You can continue.
Was there somebody? Yeah, okay. So being the largest gravitationally bound structures also means that clusters are sensitive to cosmology. So we can find them at the cosmological scale, and we can use them to probe cosmological models. But also on astrophysics perspective, that means we understand the cosmological background of galaxy clusters fairly well. So galaxy clusters are quite complicated structures themselves. They contain about 1% of stars, and then about 10% of hot gas, and finally about 90% of dark matter. These values are quite close to the universe average, and by quite close, I mean within a factor of 2. Galaxy cluster mass is enormous. That means we will have an enormous amount of stars, an enormous amount of dark matter, and also enormous amount of hot gas. These matters interact frequently with each other. We will find a variety of astrophysical processes inside clusters, and of course, that means galaxy clusters become excellent laboratories for studying processes associated with stars, associated with dark matter, and also associated with hot gas. Things are particularly interesting are star formation inside galaxies, gas dynamics, and also the dark matter interactions. And finally, we can also use galaxy clusters to learn about dark energy. So there are many ways to observe galaxy clusters, but one good way, one especially popular way of doing this is to observe them at the optical wavelength range. When we observe galaxy clusters with optical telescopes, we are directly observing this 1% of stars. Well, with this 1% of stars, or some people will say 1% of galaxies if you are referring to the stellar content of galaxies. So with this 1% of things, we can study the interactions between galaxies. And because galaxies trace the distribution of dark matter, we can also use these galaxies to study large-scale structures. Another thing that makes these optical telescope observations interesting is that the galaxy images will be gravitationally lensed around clusters. Therefore, we can also trace the dark matter distribution directly with the images from optical telescopes. So galaxy clusters are actually very rare. The number density is around, well, depending on your cosmological model, the number density of galaxy clusters are below 10 to the minus fifth per cubic megparsec. This means if you really want to find a cluster, on average, you will have to survey a box that is 50 megparsec on each side. The figure on this slide shows the number density of galaxy clusters in two cosmological models. The right one has dark matter and dark energy, and is pretty close to the standard LambdaCDM cosmology. And the second one there doesn't have dark energy. But anyway, in both cases, galaxy clusters are really rare, number density below 10 to the minus fifth solar masses. And, well, as you can already see, the mass measurement of clusters and their abundance is sensitive to these cosmological parameters. So being extremely rare means that if we want to get statistically robust study, if we want to perform statistically robust study about clusters, we will need a large volume. So large area will give us a large volume, and deeper depth will also give us a larger volume. These two things are our best friends for studying galaxy clusters. The Dark Energy Survey is one of these projects that gives us both the large coverage and also the deep depth. So on average, DES needs about 0.1 to 0.2 degrees squared to find one cluster. This is about the size of one moon. And you know, for these other smaller surveys, their total coverage is only a few times larger than that. We are also very deep. That means 24 magnitude in GRIZ. So originally, we thought that we can find clusters all the way to redshift 1.0. But because of the observing schedule now, you know, a more realistic estimation is find the clusters all the way to redshift 0.9. Beyond redshift 1.0 and all redshift 0.9, the brightest part of the cluster galaxy light has shifted to the infrared wavelength range. So you will need somehow an infrared telescope anyway. But you know, DES has this coverage to give us the statistical power, and it also has this depth to allow us to do all of the things that we can do with optical data. So, you know, it's really the dream machine for studying galaxy clusters in the optical wavelength range. So 5,000 degrees squared means we will have up to 20,000 to 50,000 clusters by the end of the survey. It's a large number that can, you know, can make us do some really statistically robust things. So optical imaging data are not only important for just finding galaxy clusters, it also helps with finding clusters in other wavelength range, for example, X-ray. The hot gas content, which we don't directly observe with DES, they can be detected in the X-ray wavelength range because this hot gas emits X-rays. So the top three panels in the slide here shows the X-ray emissions from 3 galaxy clusters. The lower panels show their optical images from DES. Well, we can look for galaxy clusters through their X-ray emissions, and the XMM cluster survey, or the XS, is it's a project that does this kind of searching. The trick of doing this X-ray searching is that we still need the availability of optical imaging data. So whenever we see a cluster-like emission in X-ray data, this is shown on the right side of the slide. this panel of X-rays with some blue dots and with some red dots and some blue blob, green blobs on it. These green blobs, extended X-ray emissions, tend to be coming from X-rays, tend to be coming from clusters. But we also need to make sure that they did not come from nearby galaxies. So to do this, we go to check their optical imaging data and see whether or not there are clusters of galaxies there. In this case, we do see clusters of galaxies. So we know that there's indeed a galaxy cluster there. But more importantly, optical imaging data helps us determine the redshift of these X-ray clusters. One way of doing this is to just use photometric data. Well, we have optical imaging data. We go to look at the color magnitude diagram of the cluster galaxies, and through examining the locus of these cluster galaxies, we can somehow infer the cluster galaxies redshift. So this is one way of doing that. Another way, we can always pursue the redshift with a spectroscopic follow-up. But to do spectroscopic follow-up things, you still need the imaging data to determine your targets. So in any way, you will need imaging data to get your redshifts. Once you have the redshifts, things get more interesting because you will need the redshift to extract more information from the X-ray map, like the X-ray temperature and the luminosity. This will tell us things about the cluster gas dynamics. Well, more interestingly to DS is that we will have the cluster mass information from X-ray temperature and luminosity. So these three clusters I just showed were from the XCS project. We have already determined the redshifts of these clusters. We have a redshift 0.2 cluster there, and then a redshift 0.7, and we even have a redshift 1.3. These are all discovered in the DSSV data. Well, the XCS project makes use of archival X-ray data from the XMM telescope. These archival data were taken for all sorts of purposes. For example, studying galaxies, studying aging feedbacks. But we download this data and try to search for these blobs of cluster-like emissions in these images. These archival data are scattered everywhere on the sky, but we can only search for clusters when we have coverage of optical data. So on this slide, the black dots there are the coverage of the archival X-ray data. And the gray area is the coverage of the DSSV data. So for this, we can only search for these clusters in the overlapping region between these black dots and the gray area, which is not a lot. For these black dots outside of this gray area, it's not, we can't really do them. We didn't do anything with them with SV data, but now we have year 1 data from DS, and we should be able to find many more clusters in this area. So through combining DS science verification data and this archival X-ray data, the XMM cluster survey, or the XS, has found about 400 clusters with DSSV data. So depending on the quality cut, if you want only the clusters with very good X-ray measurements, you will end up with about 150 clusters. This slide here shows you the mass and the redshift distribution of this sample. We cover a large redshift range. Of course, we have clusters at low redshift, but at intermediate to high redshift things, we find stuff all the way to above redshift 1. For the mass coverage, we cover the low mass to high mass range of clusters. But I think one thing that makes the XCS sample particularly interesting is that there are 1/4 of the clusters are below 10 to the 14th solar masses. These clusters, well, you can't really find them with SPT because they are not in the right mass range for observations with SPT. For optical cluster finding, well, you find things, but these are the mass range that will give us a lot of jumps. For X-ray data, we can be quite confident that these small things are clusters. So it gives us a highly pure sample at the low mass end. So I just told you that there are many, that DS is perfect for studying galaxy clusters below redshift 1.0. In the next 20 minutes, I'm going to try to demonstrate the potential of DS using one example of the cluster central galaxy analysis. So the cluster central galaxies sometimes are called the brightest cluster galaxies, BCGs. But I think a more proper name is the bright central galaxy, also shortened as the BCG. So bright central galaxy BCGs are extremely bright, and they are in the center of galaxy clusters. So in this background picture here is this big yellow galaxy in the middle. These galaxies can be more than 10 times more luminous than other galaxies in the clusters. There are 3 other clusters in this slide, and the red arrows point out their BCGs. So, well, in all 3 of these cases, the BCGs appear to be more extended and more luminous than other galaxies in these clusters. One thing that makes the BCGs particularly interesting is that they are the extreme examples of this hierarchical structure formation predicted by our standard LambdaCDM cosmology. And by hierarchical structure formation, we mean that BCGs go through a lot of merging. So the figure on this slide is the merging diagram of the BCGs simulated 10 years ago by the Millennium simulation. So the y-axis is the look-back time of these simulations. Hello? Can you still hear me all right?
Yeah, there's some noise, but we can hear.
Yes, well, it's a little bit noisy right now because I'm in the lounge. So let me try to move myself a little bit.
Thanks.
Yes, sorry about that. So the y-axis shows you the look-back time, and the rightmost of this figure are the BCGs. So these big round circles are the BCGs. There are lines connecting the BCGs with some smaller circles. These lines means that the BCGs have just merged with another galaxy. These galaxies that merge onto the BCGs, their masses and luminosities are indicated by the size of these circles. So sometimes they are small circles, and sometimes they are dots. It just means that these galaxies are really small. So back to 12 billion years ago, BCGs are really small. There are many other galaxies that are comparable to them. But with when you evolve to as you evolve to redshift 0, you see these BCGs constantly eat up the smaller galaxies around them, and they become bigger and bigger. And their mass and size contrast is becomes larger compared to these mergers. So in the past 12 billion years, BCGs, according to this merging scenario, should have experienced lots of growth. So they are good examples of this whole hierarchical structure formation thing. Well, this merging scenario does not just exist for the BCGs. They exist for all the other cluster galaxies. So this new slide here shows you the evolution of all the cluster galaxies from redshift 1. The y-axis is the size of these galaxies, and the x-axis is the mass of these galaxies. The BCGs are these stars inside of these figures. And the right panel is a high redshift, and the lower panel is a lower redshift. These black dots are the cluster galaxies that are not BCGs. So you see that both the cluster galaxies and the BCGs have got bigger, and they have got more massive from redshift 1 to redshift 0.3. The blue diamonds are the observations of a few clusters. But compared to these other cluster galaxies, the growth of BCGs is more extreme. So it's just, BCGs are just better examples of this merging growth scenario. So and then when we go to look at the BCG growth in observations, we have one problem that the merging theory doesn't seem to explain everything. So I'm showing you a few observations on this slide now. The blue region there is the simulation again from the previous millennium simulation. So you see that it grows a lot from redshift 3, and by redshift 0. Well, one way to put it is that if you look at redshift 1, if you compare the BCG mass at redshift 1 to the BCG mass at redshift 0, its mass has grown by about a factor of 3. And when people look at this by observations, so a couple of people found that it's not that much. So about a factor of 2 by late May 2012 and late 2013. And then other people that were trying to look at it with X-ray clusters, they found that, well, they didn't find any growth. These three data points in blue. So the problem from this figure is that, well, observations do not agree with this simple merging theory. And to make things worse, observations do not agree with each other. So it's not something to panic about, but that means we just have lots of things to think through. So we know that there can be issues with this merging theory. For example, BCGs could be forming stars. And forming stars means that we add more mass onto the BCGs. And BCGs could be throwing some of their mass away. And this mass that was thrown away by the BCGs would become this diffuser component of the clusters called intracluster light, or ICL. Well, the observations can also have problems. For example, we know that the BCG photometry is actually quite difficult to measure. And some other people also doubt about the sample selection of these observations. And because these observation studies were done a few years ago, we don't quite trust their uncertainty estimations too. So, if you consider the uncertainties, we don't really know where these data points might fall on. So, well, as the problem with the BCG photometry, one thing that you might first notice is that, well, optical data processing pipeline always have problems identifying objects around the BCGs. So I'm using DS as an example here, but this problem really exists in all sorts of pipelines. Even HST Hubble data sometimes have problems dealing with this object detection thing. And this object detection thing would be a serious challenge for LSST. So clusters are crowded with galaxies, and this crowdedness problem is particularly severe for the centers of clusters. So the blue box here shows you our object detection, shows the DS object detection situation before we started processing the SV data. So in the center there, you can see several bright yellow dots missing from the object detection pipeline. These galaxies are all L-star galaxies, really bright. So if you miss them, well, you might get the photometry of these central galaxies quite wrong. DS tried to fix this issue, so we first tried to tweak the processing pipeline, and we ended up finding a lot of additional things there. And we also wrote this package to help with object detection around BCGs. After we tweaked the DS data processing pipeline, there's still one yellow dot missing at the middle there, which is shown by the white circle on this fourth figure on this slide. But with this new pipeline, with this new package to find all these blended objects at the cluster centers, we should be able to find, almost all the bright sources inside clusters. Another issue with the BCG photometry is that, well, it's really hard to get the quantities right, even if you have found all of the objects. So BCGs are really extended. The figure on this slide here shows you the light profile of the BCGs within 50 arcseconds of one BCG. So it's really extended. That means if we want to measure the total light of the BCGs, we will need to find, we will need to go all the way to about 15 arcseconds. But the data processing pipeline we use sometimes truncate the pipeline, the processing pipeline, sometimes truncate the profile at a place indicated by the red line. This is an issue for our DS data processing pipeline, and it's also very common in other data processing pipelines. So if you make this mistake, you might get the BCG photometry wrong by a couple of, well, let's say, by maybe half a magnitude. And, well, there's still a third issue. That means we sometimes don't get the sky background around the BCGs correctly. So because BCGs are really luminous, really bright, well, the sky background subtraction around BCGs usually overestimates the sky around them. So in this light profile there, you can see this dip inside black circle there. This is caused by over-subtraction of galaxies, that the photon count after processing the pipeline falls below 0. The figure on the right shows you the images of this process, shows you the processed images around the bright source. I didn't find one around the BCG, but this over-subtraction issue around a bright star is very similar to the issue with BCGs, that you just subtract too much light from the images that you see are dark halo around these bright objects like bright stars or bright BCGs. So this will certainly affect the photometry measurement of the BCGs. So I also mentioned that the sample selection might be an issue for BCG studies. So some people think that if you use X-ray selected clusters, you might be selecting the clusters that formed fairly early. Some other people think that you can't use optically selected clusters, well, because you can select a cluster according to their optical content and then study their optical content. That's just a selection bias. Well, I think all of these issues are small, but there's one thing you can't ignore. That is, the mass of the BCGs are dependent on cluster mass. More massive clusters will have more massive BCGs. So the figure on this slide here shows you the relation between BCG mass and also cluster mass. So the dependence of BCG at the cluster scale is not as strong as the dependence at the group scale, but still you have the BCG mass increasing with cluster mass. And on top of that, you would have the redshift evolution effect of the BCGs. So if you want to study the mass dependence of BCGs, you'd better make sure that you have the right redshift selection. And if you want to study redshift evolution of the BCGs, like what we are trying to do here, you'd better make sure that you are dealing with the mass dependence thing. So I just showed that the sample from the XCS, from the DSSV and XCS combination gives us a really good sample that covers a wide mass range and a wide redshift range. So, well, this is showed again on this slide here. For comparison, I'm also showing the BCG study used by Chris Liedman back in 2012. At that time, he didn't really have DS data, so he had to put together several cluster samples to study BCG evolution. The problem of this sample is that it has poor coverage of the intermediate cluster mass range at intermediate redshift. So Chris Liedman did a really good work, a good job that he tried to match the cluster mass at low redshift and at high redshift. But this also means that because his sample coverage of this mass range is not quite complete, he would have to give up quite a bit of his sample in order to eliminate this mass effect. So comparatively, our DSXC sample, provides a much better basis for this BCG analysis. So we have talked about all these issues with BCG photometry and the issues with BCG with the sample selection. We think that we can solve these issues with DS data. So after we started looking at this wonderful DSXC sample, the first thing we did was try to do a simple matching exercise between the BCGs in observations and the BCGs in simulations. So we know that the BCG mass depends on cluster mass. That means we want to make sure that we are comparing a BCG in observation. So we want to make sure that we are comparing clusters of similar masses in observations and also in simulations. So to do that, whenever we have a BCG in a cluster from observation, we go to select a range of clusters from simulations, and these masses of the clusters selected from simulations matches the uncertainty of the clusters, of the cluster mass measurements in observations. So on the left side of this panel, you have cluster mass on the y-axis and cluster redshift on the x-axis. So the black data points are the cluster mass and redshift measurement and the uncertainties from data, and the red data points are the distribution of cluster masses and redshift from the simulation. Well, they match quite well. They match so well that I have to manually offset their redshifts a little bit, so you can tell that they they don't, the data points don't exactly overlap with each other. But after we did this perfect matching exercise, we started comparing the BCGs in these clusters. So if you plot the BCG luminosities or masses as a function of redshift, you start seeing that the observed BCGs are under-luminous or under-massive at a lower redshift. So this means if the BCGs in simulations and observations are of the same mass at high redshift, observationally, at low redshift, the BCGs didn't gain as much mass or didn't gain as much luminosity compared to the simulations because they become under-luminous. So this means that, they are probably, the BCGs in observations are probably growing slower than the predictions from this merging theory. We also used another modeling method to study this topic. So we modeled the BCG evolution for both simulations and observations. And this very simple model is given on this slide here. It has a mass dependence factor, alpha, and it also has a redshift evolution factor, beta. So using this equation allows us to incorporate all of the uncertainties of cluster masses and the redshifts, and also the uncertainties of BCG mass measurements, this M star on the left side of the equation there. So it allows us to incorporate all the uncertainties using a Bayesian technique. So we constrain this alpha and beta factors for this model. The constraints for this simulation BCGs are given by these stars on this figure here. The constraints from the observational BCGs are these black data points there. So one thing that is particularly interesting, is the redshift evolution factor, beta. So if you look at the beta factor, you see that the parameter value from the simulation is deeper than the parameter value from the observation. So deeper means that the group of BCGs evolve more dramatically with redshift. So again, you are seeing that the simulated BCG growth does not match the observed BCG growth. So with this model, we can directly compute the BCG growth rate from redshift 1 to redshift 0. So the y-axis here is the BCG growth rate shown at a log scale. So a value of 0.2, a value of 0.3 means that the BCGs have grown by a factor of 3. A value of 0.3 means a growth of factor of 2. So the BCG growth from this merging simulation is shown by this blue line there, and the growth factor is 0.4. But observationally, this BCG growth is only around 0.1, and with an uncertainty of about 0.1. So this means that the discrepancy between the observations and the simulations is at a level of about 2.5 sigma. So there indeed exists a discrepancy between this merging prediction and the observation. And if we compare it to the previous observations, the uncertainties range from this Littman observation all the way to this Stott X-ray observation. So the disagreement between previous observations is gone after we consider all these measurement uncertainties. The Littman and all these Stott works did consider some uncertainties, but we can almost for sure tell that they are not quite complete, and their uncertainties will be bigger than our uncertainties because they use the smaller samples. Yes, so now the observational uncertainties are gone. But still, there exists this discrepancy between observations and the merging prediction. So we already mentioned that there could be a variety of things that result in this discrepancy. For example, BCGs could be forming stars. This is considered very rare, but very recently, Michael McDonald in 2013 reported that he found a BCG with star formation of up to 800 solar masses per year. If we don't have, 800 solar masses per year is very hard to achieve. But if you have a star formation of 20 solar masses per year, you would see BCG growth like this green triangles there. So the BCGs are going to be growing even faster. So star formation is not going to explain our observation. Another factor that can make that can change the growth of the BCGs is intracluster light. BCGs sometimes dispose some of their stars into the intracluster space. They become diffused around the BCGs, but they extend up to 500 kiloparsec. So it can be pretty hard to observe them directly. So if BCGs are throwing some of their stars into the intracluster space, if they are throwing them at about 40 solar masses per year, you will see the growth rate indicated by these blue diamonds there. That means the BCGs basically don't need to grow at all. If they are only throwing away about 20 solar masses per year, their growth will be like this black crosses in this figure. So the growth rate would be around 0.2. It would match the observations better. If you have this growth rate, you are gonna see that a large fraction of the BCG stellar mass will end up in the intracluster space. That will be about this mass inside the intracluster space will be about half of the BCG stellar mass. It will be significant. So on the other hand, Container in 2014 did another simulation that not only considered the merging of BCGs, but also it considered a series of models for intracluster light production. So he predicted that the BCG growth would be around 0.2, like this, indicated by these dark black circles on this figure. So that matches our observations quite well. So we think that intracluster light provides one explanation for our observed BCG growth. So that is what we did with DSV data. What can we do next? Well, we already have DS year 1 data, and we will have DS year 2, year 3 data very soon, and eventually we would have the whole coverage of DS data all the way to redshift 1.0. So that means we will expand the DS axial sample about 3 times, and we will see a 3 times improvement in sensitivity of this analysis. So we should tell you the ICL production rate quite well by that time. And if you use optically selected clusters, the results will definitely be much better than this 3 times improvement. And another thing we can try to do is that, we can try to constrain this ICL and this BCG star formation thing directly. BCG star formation needs us to look at the colors of the BCGs, and some people have been doing this with DAS data. To constrain ICL, well, ICL is really diffused, really faint, and they are really hard to measure. If you look at a single cluster, well, it's really hard to find any ICL there. You will see diffraction patterns from the telescope. You will see uneven sky subtraction. But since DS finds thousands of clusters in a narrow redshift beam, we can simply stack the images of these clusters right on top of each other, and you will see this smooth sky background around the BCGs, and hopefully you can find some intracluster light. So this is what I have been doing recently, and we did see that you can find the intracluster light at least all the way to about 400 kiloparsec from the BCGs. So it is possible that we will eventually get some nice constraints on the ICL fraction and complete this whole picture of BCG evolution. So, well, these are the things we can do at below redshift 1.0, and DS is going to be really great for that. But we want to be ambitious, and we want to ask the question, can we go beyond redshift 1.0? If you ask that question, well, you might first want to ask, do we have any clusters beyond redshift 1.0 in DAS data? Well, the answer is yes. I've been showing that to you all the time. So on this slide, I'm showing this redshift 1.3 cluster from XS again. So this cluster happens to locate in the DS as a supernovae field, so the data are particularly deep there. Well, because of the availability of DS supernovae data, we can find cluster galaxies all the way to M star plus 2 magnitude. That means we can even do this richness estimation for this cluster, and the richness for this cluster will be fairly reasonable. Will be a fairly reasonable proxy for cluster mass. If you can find a bunch of clusters all the way to M star plus 2 magnitude, you can even try to do cosmology with them. So DS supernovae data will be great for finding a bunch of clusters between redshift 1 and 1.5. What about DS wide field data? Well, the depth there is only helps us reach about M star magnitude. But still, we have some clusters with that data, and it is fairly obvious that we can at least see this BCG thing in the depth wide field. To help with the high redshift cluster science, we also have publicly available infrared data in the DS wide field. So WISE field is a all-sky infrared survey. So you will have when you see some high redshift cluster galaxies in the DS wide field, you can almost always find them in WISE data. And there are some also smaller patches of spacer data available, spacer infrared data. It goes to slightly deeper depth, sometimes depending on which project you are looking at, and it has much a better angular resolution compared to WISE. So this infrared data will help us with our high redshift cluster science. The highest redshift cluster I found within the depth footprint is at redshift 1.7. So this is a cluster found by the SPT people. That means this cluster is particularly massive. But still, at redshift 1.7, we can find this BCG inside this cluster. So it's quite impressive, and this is just DS wide field data. So I hope I have given an impression that we can indeed find high redshift clusters with XCS and also SPT. DS has a lot of resources to do so. We have the supernovae field, 30 degree squares. It's quite a big area for high redshift cluster finding, and the data is deep enough to M star plus 2 magnitude. You can measure cluster richness with this data set. And DS supernovae field has pretty good spacer infrared coverage. So if you need infrared data, there are some stuff up to there. As with the DS wide field, they are only deep enough to M star plus 2 to M star. And there are some spacer infrared data coverage serendipitously. But if you don't mind the low resolution, WISE data is always available for assisting high redshift cluster studies. So other than that, we also have multi-wavelength data, well, from X-ray, and more interestingly, from SPT. So maybe we can use this SPT data to try to constrain cluster masses. And we have follow-up opportunities with OSTAs about this DS supernovae field. So as what is being done now for DS clusters, well, we haven't really done that much. XCS and SPT will continue to find us high redshift clusters, but SPT will only find these massive clusters, and the XCS searches are serendipitous. That means it doesn't really cover the whole DS footprint. For searching high redshift clusters in the DS wide field, we have established this easy proposal with the spacer SSDF team. Their main method right now is to use an optical dropout thing. So they use optical data to eliminate the sources that are not high redshift clusters. And for DS supernovae, for searching in the DS supernovae field, we are in contact for ESIS by a couple of spacer teams. So I think it's a great opportunity that external collaborators are trying to find us to make use of DS data But if they use the optical matching method, if they use an optical dropout method, or even if they use a optical matching method, they still do not make full use of the DS potential. And as a DS person here, I would like to see some people doing more on that. So as with DS wide field data, if you want to do high redshift cluster sorting, and if you want to use some wide field infrared data, we do have WISE data available. There has been researches about trying to look for high redshift clusters using optical dropout method, but there should be a better way of combining DS data with WISE data and then do high redshift cluster sorting. For the DS supernovae field, we have deep dependent data and we have public spacer data, and we still need a better way to combine the data. So specifically, if there are lots of opportunities in this field, and I really want to encourage some of you to pursue them. And if we have high redshift clusters, can we do cosmology with them? Well, the answer is likely no. But we can use these clusters to prepare for the next stage of cluster cosmology analysis. We might not be able to obtain a cluster mass estimate of 20%, but with SPT data, we should be able to obtain some estimations of cluster masses. And we can study the galaxy evolution inside clusters. We can test whether or not our cluster finding algorithm at low Z still works or not with high redshift clusters. And especially, since we can find all the BCGs with DS data, we should be able to use high redshift clusters for BCG studies. We can measure their growth directly, and we can also try to probe their star formation. So yes, so I hope I have demonstrated to you that the BCG studies are interesting enough, and it is definitely a scientific case that we can try to do with high redshift clusters. So that's all I have to say today. I will try to see if you have any questions.
Okay, so thank you very much. And we have time for questions.
Okay, this is Basilio here. Can you hear me well?
Not quite.
Oh dear. Okay, so I'll use the chat. I have a question ready.
Mm-hmm.
So we have
the question is.
Can you read it?
Yes. So the question is, there are cases of extended X-ray emissions that were not associated to any optical galaxy clusters or groups. Well, that would be really interesting. So far we haven't found any, I believe. And nearby galaxies can also have this extended X-ray emissions. But if we have optical data, that's pretty easy to eliminate. If we have extended emissions that are not associated with any optical structures, that will be really interesting, but we haven't found any. And the next question is, what is the linear structure of X-ray sources in one of the initial slides? Let's see. Is it this one? So,
yeah,
well,
on the right of this image, on this plot, there is a linear structure. Is this the galactic center? What is this?
Well, actually, I don't know, because these data are iCargo, so likely they might be searching for, something like agents. That's more likely. Yeah, good question. I don't know. They were probably not taken for galaxy cluster purpose.
Okay, more questions?
Yes, I have a question about your pessimistic conclusion about doing cosmology with high Z clusters, Z larger than 1.
Yes.
Why is that? Because you don't have enough statistics. You cannot actually compute the mass function or estimate the mass function.
Well, I would think that this is not a pessimistic conclusion. This is not something that has been done yet. And we are very far away from being able to do cluster cosmology at a high redshift. But DS should help pushing one step further on this. So, you know, cluster cosmology is not that easy. It's just we should be able to help doing this, although we might not be able to get reliable estimation at this moment. So as why we doing cosmology is not a particular idea. This is because the lack of cluster mass estimation at that high redshift. So for below redshift 1.0, we have weak lensing, but for above redshift 1.0, you don't have many background sources, and they're really thin. So measuring their shears is not a very viable thing to do. So weak lensing measurements likely won't be available. So that means, you know, the power of doing cluster cosmology is largely gone. We can try to do some mass estimation with SPT, but I doubt that it might not be enough. It's something that is that can be tried, and it will definitely be a next step towards cluster cosmology.
Okay.
The main reason is lack of weak lensing.
Okay. So another question is that you mentioned the comparison and matching with some simulations. So what simulations did you use?
This is the Millennium simulation from 10 years ago. It has a large volume, so it is still very useful.
Okay, but it has no baryons, right?
It has no baryons. That's right.
So how do you, because in one of the plots you had luminosity, and how do you estimate the luminosity then?
Yes, right. So the luminosities are estimated with a semi-analytical method. They try to tag the stellar content to the dark matter halos. They estimate the star components analytically according to the dark matter distribution. And usually this works pretty well if you are only thinking about the merging of dark matter halos and therefore the merging of the stellar component inside these dark matter halos.
Okay, thank you.
More questions? Okay, so I want to thank you, Yuanyuan, again. So very nice talk. And thanks everybody thanks everybody for attending, and see you all soon.